So as a part of this QBlock Challenge kickoff, I will talk about how we can use quantum computers for quantum chemistry. So let me first explain what our quantum chemistry calculations are used for in the first place. So the example number one is we used this calculation as a microscope for probing atomic structure of the molecules. This is because the foundation of chemistry is built on identifying molecular structures, but this task is very difficult. For example, there has been many misassignment of these molecular structures, and there's a review paper on this subject. For example, this molecule has been thought of as to having this structure for 10 years, but after the 10 years it has been claimed that this structure was a true form of this molecule. And this task is very important in chemistry because if we know the molecular structure, then we can synthesize those molecules. For example, there's a natural molecule that is unknown structure, but if we know the structure of that molecule, we can synthesize it artificially. So this structure identification task is very important in chemistry, and often these calculations can help to identify those structure of the molecule. Example number two is more intuitive maybe. So we can perform virtual experiments using quantum chemistry calculations. This is required because the number of molecule is very large. Because even if we restrict ourselves to the potential pharmacological activity, there's a molecule over 10 to the 63 order. So it is not practical to perform experiments for all of those potential species. And so we have to screen which molecule has more potential with quantum chemistry calculations in the first place. So this is a very important task for quantum chemistry. So as a result, we use high performance computers for chemistry problems a lot. It has been said that this around 40% of supercomputing time is spent on molecular simulation. So we have 40% of whole supercomputer time for computational chemistry. This is a lot. So we want to use quantum computers to accelerate the quantum chemistry calculations. The central problem in quantum chemistry is to find the ground state of Hamiltonian, which means we want to find the smallest eigenvalue and eigenvector of this operator. So this is this initial Hamiltonian, which have n electron inside, and this is a kinetic energy term, and this is a interaction term, and this is a potential term. But this stands for a continuous operator, so we have to discretize it to use it on the quantum computer. So first we do a second quantization using molecular orbitals obtained from, for example, Hartree-Fock calculations, and we obtain something like this. After obtaining this second quantized Hamiltonian, we can just transform it by fermion-qubit mapping. For example, we can use Jordan-Wigner transformation and to get a Hamiltonian in this form. So this Hamiltonian is just a sum of Pauli operator. So we can easily use this Hamiltonian on the quantum computer. So this whole task can be done by, for example, we can use an open source library called Hamiltonian, and also there should be other ways to do this. So this is not a problem. We can just concentrate on how we solve this Hamiltonian on the quantum computer. And the naive way of solving this problem is to use a quantum phase estimation algorithm. So this quantum phase estimation allows us to sample eigenvalues or eigenstates of a unitary U. And so this quantum phase estimation algorithms, the circuit looks like this, where we use many of the controlled unitaries, and we use a quantum Fourier transform. To use this circuit for this Hamiltonian eigenvalue problem, we can just set U equals exponential IHT. Then we can get eigenvalues and states of the Hamiltonian of interest. But the problem is this quantum phase estimation requires large number of gates, and it is unlikely to be implemented on NISQ devices. So as an alternative, there's algorithms called variational quantum algorithms, and where we use a parameterized quantum circuit U theta, and we run this circuit and generate the state here, and we measure this circuit, measure this state, and we obtain cost function in the classical computer, and classical computer tries to move this parameter theta to minimize this cost function. We can use this framework for quantum chemistry, for example, but we can use optimization, the machine learning, and also other tasks. This framework allows us to use effectively the shallow quantum circuits, because we can just structure this quantum circuit as a hardware compatible circuits, and we can optimize this circuit to do something that we want. And the variational quantum algorithms, the quantum chemistry version of the variational quantum algorithm is called variational quantum eigensolver, and which is an algorithm for searching the ground state of a quantum system. And this works like this. So we run the quantum circuit U theta, and we obtain a quantum state U psi out, and we measure this expectation value of Pauli operator that appears in the Hamiltonian, and we combine this expectation value on the classical computer to get the expectation value of this Hamiltonian, this target Hamiltonian. And we want to minimize this H theta because we want to find ground state, which is a minimum energy state of this Hamiltonian. So to minimize this expectation value, we update this parameter theta, and we iterate this loop until this parameter theta converges to some certain value. If this theta converges to, for example, theta star, then this psi out theta star is approximate ground state of the Hamiltonian. And from this ground state, we can obtain the information of the molecule. For example, we can draw a electron density of the ground state. But so the VQE has been promising candidate for this NISQ algorithm, but we are kind of becoming aware of problems of VQEs, as you may know. And the first problem is that it is very difficult to optimize the parameters under this statistical noise that is intrinsic on quantum computer. For example, the state-of-the-art optimizers for VQE can only optimize very small molecules using 10 to the 8 shots or runs of quantum circuits, and it costs us, if you use a real hardware, real quantum hardware, it costs us $1 million. So right now, only a millionaire can afford the VQE of ammonia molecule, for example, using real hardware, which is very small molecule. And the second problem is that it takes too many shots to obtain accurate energies. So there's a paper that estimated the number of shots that is required to obtain accurate energy, and they basically show that it is kind of impossible to obtain accurate energies, because we have to run days to get accurate energy. We have to run days of quantum computers to obtain accurate energies. So let me finally summarize some of the recent studies to improve this VQE. One direction is to develop specially designed optimization algorithm. For example, there's a paper from Ellen and a group, and also there's a paper from us too. And another strategy would be to develop an alternative measurement strategy to reduce the measurement count to obtain this accurate energy of the state. We also have work on this, and there's many papers on this subject too, which you can check to improve your shot counts. Also, to improve the result obtained by VQE, we can combine it with Monte Carlo method. For example, there's a method that combines the VQE with the variational Monte Carlo inspired techniques, and there's a recent paper from Google that combines VQE kind of task with the quantum Monte Carlo methods. And also we have to construct more effective answers, and by effective, for example, we have to be able to easily optimize these answers, and these answers should be able to create the ground state of the system of interest. There's not many papers on this subject, but there's a paper from Kyoto University, and there's a recent paper from these guys too, using ideas from the tensor network. So maybe you can check these ideas to improve your VQE result in the skill park challenge too. So to summarize, this chemistry is a big interest which uses great amount of computation, but promising algorithms such as VQE have certain problems that has to be overcome for practical applications. So we are seeking fresh and nice ideas for applying NISQ to chemistry, and we don't want you to restrict yourselves to VQE. You can use quantum Monte Carlo technique and quantum variational Monte Carlo technique, and also, for example, you can use classical state-of-the-art techniques before the VQE. So So this challenge is just you can do anything. You can do anything as long as you use a quantum computer. So good luck with the so good luck with this QPUB challenge. And this is with that I would like to end my talk.